Alright guys, it's everything you never wanted, me teaching you through a computer screen again. But here we are, and we gotta learn chapter 4, electromagnetic waves. You've heard of this before whenever we talked about the Big Bang Theory. This is a type of transverse wave, which is the one that does the whole up and downy thing. And it involves the transfer of electric and magnetic energy. So basically they took like that much creativity with naming these things because, as you can very plainly see, electro, electric, magnetic, magnetic, okay? And you should know at this point that waves all transfer energy. They don't transfer matter. And one of the easier ways in the last chapter we discussed that you can see they transfer energy is the rubber duck floating on a wave, because the rubber duck would just bob up and down, whereas if a wave transferred matter instead of just energy, it would move the rubber duck along with the wave. But that's not how that works. So they transfer electric and magnetic energy. And I'm not going to play the videos in this video just because that's probably some type of YouTube copyright no-no. And they're all on Google Classroom, so you can watch them whenever you want to, because they're basically going to go a little more in depth with everything I'm telling you and pretty much tell you the same stuff that I'm telling you, just with somebody maybe you'd rather listen to more, or it has more interesting visuals and pictures for you. But they're there if you want them. Alright, through the magical power of editing, Mr. Matlock has appeared and is going to be gracing us with his presence and input in our lecture, because what's better than one science teacher you don't want to listen to?
Two science teachers.
You don't want to listen to, and a partridge in a pear tree. As we were just saying, this is your electromagnetic spectrum, and yes, sadly, I'm going to make you have to memorize it because, yes, as I've said before, the easiest way in the world is to memorize this starting in the middle with your visible light portion, okay? You all know your colors of the rainbow with red, orange, yellow, green, blue, indigo, violet. Once you've got that on lock, the rest of this is a little bit easier to try and tackle. So with red, literally right here with red, you have infrared right beside it. Violet. Nobody says their favorite color is violet. Their favorite color is purple. No human has ever told me their favorite color is violet.
Mm-hmm.
So,
indigo was mine, actually. So.
Okay, he's voted off the island. So over here with violet, you have ultraviolet. So again, keep in mind, having someone say their favorite color is red is normal. Radios are normal. Microwaves are normal things. And then, of course, you have infrared. Over here with violet, you have X-rays, which I pray for most of you are not normal things that occur in your day-to-day life. And then you have gamma rays, which again sound like something that fell out of a comic book. So these are kind of your abnormal things. And if you can look at the wavelength here in our beautiful, lovely little transverse waves, if you can remember that radio waves have the longest wavelength and gamma rays have the shortest wavelength, you can kind of piece together how to memorize this stuff.
And if you look at which ones have the most energy, obviously the Incredible Hulk, who was exposed to gamma radiation, he had all that high energy, high frequency, so that was a dangerous thing. I wouldn't want to be exposed to that.
No, that's going to damage you ever so slightly. Hence the other reason why in X-rays they put that lovely lead apron, as many of you have commented on the poor lady whose picture is in our textbook wearing the lead apron, have seen. With, again, electromagnetic waves, and you can totally read the rest of this title because our picture is definitely not blocking it. They are made of these vibrating, as we addressed before, electric and magnetic fields. Remember, they took no effort whatsoever in naming this stuff. So they move through space or a medium at the speed of light. And that speed of light part is technically actually only their speed through space. Whenever they hit a medium, their speeds will change just a little bit.
And that would be called refraction if it hits in an angle, correct?
Yep, and that is when it bends. You are correct. Little review there. We are very, very, very grateful that these are electromagnetic waves that are able to move through space and not mechanical waves that we discussed in the last chapter. And that's because if they required a medium to move through, we'd probably be a little dead. Mostly because we would have no idea that there was a sun, we would not be able to feel its heat, And without those two things, life kind of sort of ceases to exist. If we pretended
Yes.
that wasn't an issue in our very pampered, cushy lifestyle that we've become accustomed to, we are completely and totally reliant to an extent on electromagnetic waves and their ability to move through space.
I have a call coming in. This is a text. We thank Brandon for joining us today. Brandon notes that electromagnetic sounds like electricity and magnetism. So maybe that's how they hook. Very good point, Brandon, and thank you for joining us today.
Thank you, callers. Without your support, this video would not be possible, and our whole 5 subscribers. Subscribe out of pity if you want to. If not, we completely understand. We've had to watch these back and edit them. So the second bullet point on here I feel is sort of unnecessary and just a little extra. Hence the reason there's not a rainbow beside it, because it's a little extra. But to give you some more information, the movement of these charged electric and magnetic particles are pretty much going to generate more electric and magnetic particles, which is why this type of wave can kind of go on forever. Literally any radio broadcast, microwave broadcast, TV program, anything that's pretty much been shot out into the ether is still going out there. There was a cute little movie or TV show. I don't remember too much about it because I think I was too old to actually watch anything but previews for it. But there were signals being sent out from the 1950s, like I Love Lucy episodes, commercials, cars, and that kind of stuff. And some little alien planet was able to pick up all those radio signals. And whenever the astronaut reached there, they were living like they were in the 1950s, which, if any of that were possible, could actually totally completely happen because those broadcasts are still out there in the universe somewhere, which again, because they can travel through space, which is an empty vacuum, and there is no medium or matter there. And we're grateful for this.
Definitely. And they can travel through liquids and different mediums as well.
Oh,
yeah.
I think X-rays definitely prove that extremely because they kind of go through your entire body and show your broken, sad little bones. Or, as we'll see in the PowerPoint, some other interesting things that can sometimes be lodged in humans.
You know, it's kind of scary when you think about it because you always have, all of us have radio waves traveling through our bodies right now.
24/7. So if you'll notice, it shows that yellow wave is traveling along your X and your Y axis, and it's got that purple one going along your Z axis.
And once again, you see how science and math work together. You're talking about the right angles, you know, the total 360 would be all the way around, and a fourth of the way is that right.
That's your little Greek letter lambda. That means wavelength. You can see it here literally going from crest to crest on the electric field wave. So again, little review, just be aware.
And you can see the horizontal wave and the vertical wave have the same wavelength.
All right, so electromagnetic radiation, this is literally the energy that electromagnetic waves transfer. So it's basically a name for an electromagnetic wave.
I've actually seen this question. I believe it was on the test at one point.
There should be a rainbow by then. Oops. It is very redundant because, as we said on the first slide, the only thing that waves transfer is energy. So an electromagnetic wave is going to transfer electromagnetic energy, which they decided to name radiation in this case. Yay, more redundancy.
So when you talk about radiation, do you think that's where they came up with the word radio?
I would say it'd be a great possibility. Yes. It would not surprise me. We're going to argue a little bit in science because why on earth would anyone anywhere agree on the exact way that the universe works? Because that's all science is trying to do is explain this. So we're going to argue a little bit, not us, the scientist, about what light itself looks like. And we've got 2 models to do this with. We've got the wave model, which light is literally going to look like a wave. Okay? And we're going to talk about this thing called a polarizing filter. When light passes through one of these polarizing filters, will it have the property of a single wave? Otherwise, it's going to be waves that are going in all directions. Imagine the picture you just saw of the 2 waves that were going one like this and one like this, times like 12, and then rotated in all different angles is sort of what light's going to be doing with all those different wavelengths from your reds, orange, yellows, blues, etc. So what this polarizing filter is going to do is it's literally going to filter and only let one of those wavelengths through. If you have polarized sunglasses, That's what those are doing. This image right here is going to show that polarizing filter. You can literally think about it like a picket fence. This is the example I used in my class, as much as I hate to admit it. But imagine a giant picket fence. If you wanted to go through the fence, you would simply move side to side through the fence, and then there would be that cartoon moment where someone would turn literally like this and try to go through the fence and hit it, and that would be the comic relief. That's what's happening to all the other waves. It's not allowed to go through it. For those of you who have no idea what polarized sunglasses are or polarizing filters are.
Miss Peak, I was experimenting with some gamma radiation.
Oh, I thought you were just bored to death.
I feel a little strange.
You look great.
Oh, thank you.
You look great. So for those of you that have polarized sunglasses,
Yes, I bought some at Walmart, and they actually help you see a little bit under the water. So like if you're fishing, it does seem to help.
Yeah, and the more pricey ones like Oakley's, they help a ton. Anytime you've been out on the water in the pool and the sun has hit that and that horrible glare thing where you can't really see, they will literally filter out a lot of that light and you can see almost straight through to the bottom, which is why it is so helpful with things like fishing.
And I've noticed at this time of year, when I'm coming to school, if the window's a little frosty, the window really has to be really clean because if the light from a street light or an oncoming car hits that, it's just almost impossible to see. So yes, I can see where this would be very helpful.
Absolutely, and that's what that whole polarizing filter and polarized light means. It just literally means light that has gone through a filter, so only one wavelength is traveling through it that you can see.
I've also noticed, the picture was like the picket fence, the waves would go through it in one direction, but they also have like a lattice work where it's in two different directions, and that blocks a lot of light, very hard to see through. Yes. So that would work great for a privacy fence.
And again, over here, the thing that looks like the Pink Floyd album here, that is just showing a prism breaking light up into all of its different wavelengths, again, the reds, orange, yellow, greens, blue, indigos, violets, because light is a spectrum as well, just like the electromagnetic light.
Okay, I see the light is hitting at an angle, and so that makes the light break into the different colors. If it were hitting it straight on, would it then still continue to look like a light until it was exiting?
Most likely. I do think most of the time prisms use refraction and cause that light to bend and break apart and make that pretty rainbow effect.
Because I remember kind of going back to our review of refraction, it seemed like things had hit at an angle, like the straw into the glass of water.
It's because whenever it hit that second medium, so it going through air, which is a gas, and then hitting the solid that is what caused that bending to end up happening, is it would change speeds when it went from one medium to another. So
sounds good. Just as an extra review for you guys.
Just because we really want you to bond and love these waves just as much as we do.
Yes.
Because we're totally not ready to talk about earth science at all. Our second model that we are going to picture light as is going to be the particle model. And on this one, I feel as though it's one of the easier ones to visualize instead of the billion waves having to go through a filter. They literally want you to picture light as thousands of millions of billions of little tiny packets beaming through the air. Okay, that's exactly how they want you to view it. High frequency light, like violet and ultraviolet, if you'll kind of picture that electromagnetic spectrum in your head again, remember it had a lot of energy. It's why it had a high frequency. It can hit metal and knock some of the electrons off of it. If you've forgotten what an electron is, it's one of the three subatomic particles that make up an atom. You got your protons with a
positive charge.
You got your neutrons with a
neutral charge.
And you have electrons with a
negative charge.
Absolutely. And easiest way in the world to remember that is protons start with P and are positive. Electrons have that little dash in the middle, just like a negative sign. They are negative. And neutrons start with NEU and are neutral, just like neutral is spelled NEU. And neutral is literally even written as a circle with a slash through it. So if you put the N for neutral and the circle with a slash, it literally looks like no for no charge.
And this is one thing that a lot of students mess up a lot.
Again, those high frequency ones can come in contact with metal and displace some electrons.
And one thing that kids, going back to a review, a lot of times they get mixed up. They think the proton is positive and the neutral is negative. I don't know why people think that, but they always think about that neutral as neutron, neutral.
Because again, they had no creativity in naming that.
No.
So that is just a fancy word for your photoelectric effect. And hopefully you know the prefix photo means light.
Yes. And then so you have light and you have electricity, electron. Oh, light, knocking off electron, photoelectric
effect. And again, those little itty bitty tiny particles or packets of light they're wanting you to picture in this model, they call them photons.
I used to watch Star Trek and they would shoot their photon torpedo and it would go, have the lights. Oh, another question from Brandon. I'm really enjoying the video. What do the little rainbows mean? Oh, the good question, Brandon. Thank you.
Those are going to come back to haunt you sometime around probably test day, if I had to guess. And again, thank you for liking, subscribing, and praying that we never make another one of these. Yeah. But those little tiny packets of light are called photons. That's just their little fancy name because, of course, why couldn't we just call them the light packets instead of having to give them yet another vocabulary word and name?
Once again, the Greek prefix, photo. That's really handy, when we passed out the Greek prefix
and suffix sheet. That is totally going to be in your notebook because you were going to have a notebook test as your final test grade for me this 9 weeks. I know you're excited about that.
Same here.
Here, instead of this saying light model, this should actually be saying particle model of light because it's literally wanting you to picture the light as little tiny particles kind of being shot out of it, for lack of a better way to describe it. And your photoelectric effect, these particles are going to strike metal and discharge electrons which have a negative charge, which is why those little yellow circles have that dash in the middle. And it's that simple.
So if it knocks an electron off, going back to your chemistry, then that's going to leave too many positive or protons.
Correct.
So then it would have
that would become an ion. So that would make it have a positive charge overall. And believe it or not, guys, that's the end of section 1. You made it. Hopefully you're not cringing too hard because we certainly are. But there will be 2 more. Yes, 2 more of these beautiful, lovely videos for you to watch for the other 2 sections in this chapter. If you have questions, we understand. We probably made more of those questions than we answered today. Feel free to email us about them, put some comments in Google Classroom, or on this YouTube video that you hopefully are not going to judge us too hard for.